Next speaker is Brendan Cole from Wesleyan University. He worked under the guidance of Bob Harmon from the Department of Physics and Astronomy here at Ohio Wesleyan. And he also collaborated with Katie Gray from Whitman College and Josh Jennison here at Ohio Wesleyan. And as you can see, we have a team effort here for the presentation. So actually Brendan and Katie will be presenting this morning. Thanks.
So like Dr. HK said, I'm Katie Gray. And this summer we were studying star spots on the star LO Pegasi. This is an image taken of sunspots, which are analogous to star spots. They're the cooler, darker regions you can see right here. And they're found in areas of strong magnetic fields, where the magnetic field is perpendicular to the photosphere, which is the visible surface of the sun. So they're closely linked to the solar weather of the sun. And by having information about other star spots, we're hoping to better understand the magnetic activity of our own sun. So if you have a conductive loop that's moving through a magnetic field, then according to Ohm's law, which is up here, the current I is going to be equal to the EMF over the resistance R. And then Faraday's law also tells us that the EMF is equal to the change in flux over time. So because the current is inversely proportional to the resistance, if you take the limit of an infinite conductor that has a resistance of 0, then you would get an infinite current. This doesn't happen in real life, so that requires that the EMF is equal to 0, which again, according to Faraday's law, requires a constant flux. And this is what's called flux freezing. And what happens is as the loop moves, the field lines will actually move with the loop across so that there's no change in flux over the loop. And this is what happens in the sun. So the sun and other stars are made of plasma, which is just ionized particles, ionized gas, so that it's very highly conductive. So if you think of parcels of plasma, then as they move around the sun, the field lines will bend and move with them, like so that you prevent changes in flux. So in the plasma, there are two main competing forces, and those are due to magnetic fields and gas pressure. When the magnetic tension is a lot smaller than the gas pressure, then the magnetic field lines follow the plasma, and this is when flux freezing happens. And this is what happens in most of the photosphere. However, in star spots, where the magnetic tension is thousands of times stronger, that's when the magnetic field lines become rigid, and they don't bend well. So instead of moving side to side, the gas particles can only move up and down. And this kind of demonstrates that. So here you have most of the photosphere, where there's flux freezing happening, so the field lines are moving with the plasma. And the main form of heat transfer here is convection. And convection is a circular motion, so it requires side-to-side movement as well as up and down movement. And in this region, in the star spot region, the particles can't move side to side because of the strong magnetic field lines. If they did move side to side, that would create changes in flux, which would lead to that infinite current impossibility. So the particles instead move up and down along the magnetic field. So the main form of heat transfer is radiation, which at the photosphere is a lot less effective than convection, which is why those areas are cooler and also darker. So this is the Babcock model of the solar cycle. Our sun experiences differential rotation, which means that at different latitudes, the plasma has different angular velocities. So around the equator, the gas is moving faster, and because of flux freezing, the field lines are trapped in the plasma. So that creates this twisting of the magnetic fields. And the magnetic field lines are in areas that are called magnetic flux tubes, and they're buoyant. So sometimes they surface. And in this image, you can see a little surfacing of the tubes, and where they intersect with the photosphere is where you get star spots.
And now I'm going to talk about what we do once we get an image from our telescope and our CCD camera. This is the type of image that we'll usually start out with. Two things to notice are that mostly in the center here, there's a lot of noise, and we want to get rid of as much noise as possible to make sure that we're actually measuring differences in the star's brightness instead of in the sky or the background or something like that. And also, there's what's called vignetting, which means in the center here it's a lot better illuminated than on the edge, and that's mostly due to effects within the telescope. And we also want to account for that. So how we do this are three main things. The program we use is called Miro Pro 7, and we use that to calculate the air mass, which is essentially the amount of air that the light has to go through in order to get to our telescope. And we need to know this to know that the more air the light has to go through, the more scattering that's going to happen. So that helps us understand how much the star will be distorted. We use what are called dark frames and flat fields also. Dark frames help account for the amount of thermal noise that's going to be present in the image, and since the CCD chip is not at absolute zero, even though it is cooled, there's going to always be thermal noise. And then flat fields are what we use to account for the vignetting that you saw before and the sky background. And so once we produced an image, it goes from this is the image that you saw before, and then that's the type of reduced image that we get. So you can see there's much less background noise, and also there's barely any vignetting present. Once we have our reduced image, we do what's called differential aperture photometry. And for this, we need to compare the brightness of Elo Pegasi to two other stars to make sure that it's varying and not the effects of the sky. These two other stars are called our comparison star and our check star, and they are SAO 89758 and GSE 2188 1044. You can see Elo Pegasi is here, our comparison star is here, and our check star is there, and they're very close in the sky, so we know that if one or both of these two is varying, that probably means that there's something varying in the sky itself that's causing the distortion and not Elo Pegasi. Once we know how much Elo Pegasi is actually varying, we can create what are called light curves. We know that it rotates about once every 10.153 hours. So we can use the fractional part of its rotation, so if it's rotated like 41.5 times, its rotational phase would be 0.5. And you can notice one thing, that these magnitudes seem to be going backwards, and that's because for astronomers, a lower magnitude means a higher brightness. So going up on this plot actually does mean higher brightness, and going down on it does mean lower brightness. Another thing is that this R and this V are the different two of the different filters that we use, and we use different filters so that we can tell more about the star than we would be able to with just one filter. And what those light curves tell us, are, especially that one there, is whether there are spots on the star or not. So that if there were no spots at all, the surface wouldn't vary at all as it rotated with respect to us. So we would just expect a flat line on that plot instead of the quasi-sinusoidal curve that we saw. And then the period of light curve also tells us approximately where the spot is on the surface of the star. So you can see here if there's a polar spot, and Elo Pegasi is likely inclined towards us. So if there's a polar spot, as it rotates, you're always going to be seeing this spot. So the star is going to be dimmer overall, but it's not going to change very much over time. Compared to this, or especially here, as the star rotates, we're going to see this spot for half the time, and we're not going to see it for another half the time, which means we're going to have a large variation in the light curve. We plan to use what's called light curve inversion to create a model of the surface of the star. So briefly, over the last few years, you can see there have been spots in different spots of the rotational phase each time. And then in 2012, you can see there are kind of two different curves here. These down here were mostly from earlier observations, and then these are from later observations, meaning the star actually probably changed between the summer and the fall of 2012. And also it's dimmer overall, meaning that there's probably a polar spot that wasn't recognized. And how we know there actually were spots is that if a star is cooler, it's going to be a little bit dimmer, and therefore it's going to be a little bit redder. So we can check the difference between the magnitude measured in our B filter and the magnitude measured in our infrared filter to sort of get a measure of how red the star is. And you can see that as the star gets brighter overall, it gets less red, meaning that it's hotter and there's not a spot in the way between it and us. And so we would expect these to be about 180 degrees out of phase if there was a spot, and that's what we see. So that gives fairly good confirmation. And then this is our data from so far this year. You can see that it is a little brighter than it was in 2012, and also there is a dip here, about comparable to that in earlier years. And what we'd like to see in continuing observations is to complete the light curve by getting some data here, and then also to just get a more complete light curve so that we can do this inversion method that Dr. Harmon has developed. So thank you. Are there any questions?
Questions or discussion?
There were some orange points on one of those curves that looked really, really funny. If you go back. Yeah, those
Yeah.
ones.
Oh, these?
Yeah, what happened?
It was probably just some sort of distortion in the sky that we didn't account for. Yeah.
That goes along. I was just going to ask, I was curious, you talk about these reference stars that you use to tell whether there is some sort of distortion in the sky. So is there some, apparently you don't always just throw that data out. I'm assuming you just try to subtract that reference signal.
Yeah, so they are named different things so that we tell the program what the magnitude of that one is so that it has something to compare to, and then if we see something weird going on with the brightness of L Pegasi, we can see if we see the same weird thing going on with the check star in order to figure out if it's something weird going on with L Pegasi or the atmosphere. So we use sort of this star to calibrate our numbers, and then this star to make sure that the numbers are correct instead of changing.
And then if there is something weird going on, do you just throw out the data, or do you just assume, you make an assumption that the sky is sort of homogeneous and whatever distortion is going on at that point is the same?
Yeah, so these are very close together in the sky. So if there's a distortion going on right here, it's very likely that it's also going on here and here.
So that usually works.
Yeah, so this helps to correct for that. And then if there's too much, then the data is probably unreliable.
So LO Pegasi has differential rotation. Does the 10-hour period, does that correspond to like an average rotation of it? Or?
I think it corresponds to the equatorial rotation.
We don't have strong evidence for differential rotation on that star.
Okay, let's thank both speakers again.